In the last video, we saw the concept of quantum parallelism with the help of the oracle gate UF, whose transformation is given as when UF operates on xy, we get x and y XOR f of x, which is represented by this diagram. In this video, we will see the Deutsch algorithm to solve the given problem. Suppose we have a function f of x from 1-bit domain to 1-bit range, and we have to check whether the function is a constant or balanced. Now before solving this problem, let's see what is a constant function and a balanced function. Function is called constant when for the values of x 0 and 1 the function gives the same value, that is either 0 0 or 1 1, which implies that f of 0 will be equal to f of 1. And a function is called a balanced function when for the given value of x 0 and 1 f of x is either 0 1 or 1 0, that is the value of the function is balanced. Now with the help of Deutsch algorithm, let's try to find whether our given function is constant or balanced. So Deutsch algorithm combines quantum parallelism that we saw in the last video with quantum interference. It is the first and the simplest algorithm in quantum computation. So now let's see its working. So the given quantum circuit is used to realize the Deutsch algorithm. This circuit is simplified by the four states psi 0, psi 1, psi 2 and psi 3. So let's evaluate each of these states. From the diagram, we can see that psi 0 is the tensor product of 0 state and 1 state. Therefore, psi 0 can be written as 0 state tensor product 1 state, which is equal to 0 1 or 0 1. Similarly, psi 1 is the tensor product of these two states, which are obtained when we operate the Hadamard gate on 0 state and Hadamard gate on the 1 state. So psi 1 can be written as h when operated on 0 tensor product h when operated on 1. When the Hadamard gate is operated on 0 state, we get 0 plus 1 by root 2 tensor product, and when the Hadamard gate is operated on 1 state, we get 0 minus 1 by root 2. FYI, the plus state is given as 0 plus 1 by root 2 and the minus state is given as 0 minus 1 by root 2. So we can write psi 1 is equal to plus minus state or plus minus also. Now to evaluate psi 2, which we can get by operating the oracle gate on the psi 1 state, which can be given as psi 2 equal to u of f operating on psi 1, where u of f operation is given as when operating on x and y, we get x, y XOR f of x. So we have psi 2 equal to u of f operating on 0 plus 1 by root 2 and 0 minus 1 by root 2. Now if you take root 2 common, which will be 1 by 2, we'll have u of f in the bracket 0 0 will give us 0 0 state, 0 1 will give us 0 1 state, and 1 0 will give us 1 0 state, and 1 1 will give us minus 1 1 state. Now using this transform, let's see what we get. So psi 2 will be equal to half. For 0 0, we'll have 0 into 0 XOR f of 0, minus for 0 1, we'll have 0 1 XOR f of 0, plus for 1 0, we'll have 1 into 0 XOR f of 1, and for 1 1, we'll have 1 into 1 XOR f of 1. Now we can simplify this further by taking 0 and 1 common. So we'll have psi 2 equal to half 0 0 XOR f of 0 minus 1 XOR f of 0 plus half 1 bracket 0 XOR f of 1 minus 1 XOR f of 1. Now suppose, let's take the first case, that f of 0 is equal to f of 1, which would be 0, which implies psi 2 will be equal to half 0 bracket 0 XOR, since f of 0 is 0, we'll have 0, minus 1 XOR 0 plus half 1 bracket 0 XOR 0, since f of 1 is also 0, minus 1 XOR 0. Now we all know for XOR gate, if x and y both are 0 or 1, the answer is 0, and if both are 0 1 or 1 0, the answer is 1. So we'll have psi2 equal to half 0 0 minus 1 plus half 1 0 minus 1. By simplifying this, finally we will get psi2 equal to 0 minus 1 by root 2, that is by taking 2 common and splitting it into 0 plus 1 by root 2. So in case 2, if our f of 0 is equal to f of 1, which would be equal to 1, we'll have psi2 equal to half 0 0 XOR 1 minus 1 XOR 1 plus half 1 0 XOR 1 minus 1 XOR 1. And similarly, by solving this, we'll get finally psi2 equal to minus of 0 plus 1 by root 2 and 0 minus 1 by root 2, which implies for all f of 0 equal to f of 1, that is either 0 or 1, our value of psi2 will be equal to plus or minus, that is this was plus and this was minus, 0 plus 1 by root 2 and 0 minus 1 by root 2. Similarly, we can check for case 3, f of 0 is equal to 0 and f of 1 is equal to 1, that is f of 0 is not equal to f of 1. We'll have psi2 equal to half 0 0 XOR 0 minus 1 XOR 0 plus half 1 0 XOR 1 minus 1 XOR 1. And in a similar manner, if we solve this, we'll get 0 minus 1 by root 2 and 0 minus 1 by root 2. And for the case 4, that is f of 0 equal to 1 and f of 1 equal to 0, psi2 will be negative of 0 minus 1 by root 2 and 0 minus 1 by, you can pause the video and check it by yourself, which implies for all f of 0 not equal to f of 1, psi2 will be equal to plus or minus 0 minus 1 by root 2 into 0 minus 1 by root 2. So to summarize the result for psi2, we have this result when f of 0 is equal to f of 1 and this result when f of 0 is not equal to f of 1. Now from the circuit, we can see that after getting psi2, the first qubit of psi2 is operated by the Hadamard gate in order to get psi3. So psi3 will be equal to plus or minus Hadamard gate operating on 0 plus 1 by root 2, that is the first qubit of psi2, 0 minus 1 by root 2 for all f of 0 equal to f of 1, and plus or minus h operating on 0 minus 1 by root 2 and 0 minus 1 by root 2, that is on the first qubit for all f of 0 not equal to f of 1 case. So when h operates on the plus state or the minus state, we have when h operates on the plus state, which is given by 0 plus 1 by root 2, we get the 0 state, and when h operates on the minus state, that is 0 minus 1 by root 2, we get the 1 state. So psi3 will be equal to plus or minus 0 0 minus 1 by root 2 for all f of 0 equal to f of 1, and plus or minus 1 0 minus 1 by root 2 for all f of 0 not equal to f of 1. Now for all f of 0 equal to f of 1, f of 0 XOR f of 1 will be equal to 0, which implies the 0 state can be written as f of 0 XOR f of 1. And for all f of 0 not equal to f of 1, f of 0 XOR f of 1 will be equal to 1, which implies the 1 state can be written as f of 0 XOR f of 1, which implies our psi3 state, which was given by this result, can be written as plus or minus f of 0 XOR f of 1 into 0 minus 1 by root 2. And this is for all the cases when f of 0 is equal to f of 1 and f of 0 is not equal to f of 1. So this was the result of psi3. So if you measure the first qubit of psi3, that is f of 0 XOR f of 1, as shown in this diagram, the result of this will be either 0 or 1. So if f of 0 XOR f of 1 gives us 0. This will imply that f of 0 is equal to f of 1. Otherwise, f of 0 would not be equal to f of 1. That means we have only taken a single measurement, which implies the quantum circuit representing the Deutsch algorithm has given us the ability to determine a global property of function, namely f of 0 XOR f of 1, using only one evaluation of f of x. This is faster than is possible with a classical apparatus, which would require at least two evaluation in order to determine whether the functions are equal for two values or not. So this in essence was the working of the Deutsch algorithm. I hope you understood it.